Hello, everyone. Thank you very much for here to see this presentation. My name is Sang-Yong Oh, and I'm economist. I have a PhD degree in economics and have a chance to learning deep learning for this semester. And today I want to introduce the research what I did during this semester. The main thing is I introduce international trade with deep learning, machine learning model. So basically, gravity model is for several decades of research on this topic in economics, specifically international trade theory. But there is a lot of lacking components and some issues well known. But I want to try to represent and figuring out what is the other method to deal with this analysis by using deep learning models. So today I'm going to talk about international trade flows predictions using machine learning model comparing to gravity model that is well known in international trade field and economics. Today's outline is like this. I introduced my motivation to research this and some introduction for the original gravity model and the data, what I use, and what kind of methodology to do this project. And I will introduce main results. So machine learning technique is more powerful in the predictive side of performance. So I'll analyze more in detail. And old method of gravity model, we're dealing with the OLS. Even in the panel data setup, there's a lot of well-known issues, but we sometimes ignore it. Sometimes, try to different method to apply for resolving that issues. That one of most well-known issue is multi-collinearity. So I will comment about that. Economics field, we are really worried about how to deal with this as a machine learning model applied to well-known gravity model. Sometimes we believe and we also think that the interpretability. So we are staying in the side of causal inference. So which variable caused the change of dependent variable and finding out the significance, and we can tell or some giving a policy implication. But in general, the machine learning models more focusing on the prediction. So lacking of interpretability, but I use Shapley value to having some more interpretability during this research. So we believe that machine learning or, I applied random forest and also neural network model to deeper predictions, but we consider them as a black box because it is not assume anything about functional relationship among the variables. So we don't have any idea how the structure relationship among them. But even though there is a lot of assumption going on the data set and all the model econometrics or statistical techniques from OLS, we applied or limited in the sense of linear model, but still does have a strong power to doing a causal inference side of it. And also it is well applied to interpretability. But machine learning side has lacking of that power. So sometimes we need OLS to see those high power of interpretability. So I'm going to compare one by one and how we can bring the more technical machine learning model to apply this analysis and how to get the implication out of those lines of models. So international trade field, we have a lot of interest about how to get the accurate prediction of trade volumes. Before that, we study a lot about how trade happens, how we can say about, what kind of thing is necessary to boost your exports and control the imports, and all those theories exist. But it is really hard to quantifying result is coming out from that. There's not that many like empirical studies in the field of international trade. Other field or other subject in economics, there is researched about quantitative side, and a lot of data is dealing with in the section of econometrics part. But recently, in the economics field itself, we use gravity model to see that trade volume is how to determine by some of variables. So the gravity model itself is basically coming off from the Newtonian gravity equation, which is gravity is determined by the mass of two objects times together divided by the distance squared. The gravity is determined like that. We inspired that physics side of idea to trade. So we believe that trade volume is acting as like a gravity. So, for example, U.S. GDP as the measure of mass of U.S. economy, and also South Korea, the GDP as the considered as mass of South Korea. So multiplication of GDP of U.S. and GDP of South Korea divided by distance of two countries will determine the total volume of trade. That's a theoretical side of gravity model. So it's been a couple of, or more than 3 decades of research on this, and it is well working in panel setup, OLS setup, like that. Availability of data set, I applied, panel regression, used fixed effect model as a baseline, and I also, applied to or more digging up the depth of it to the side of a prediction. So I applied a random forest and a neural network correspondingly. So one big part of challenges of applying the machine learning side of it is non-linearities can be dealt with it. So OLS, always we assume that linear relation. So yeah, in that perspective, it is not that difficult to gravity model is, multiplicative of two countries' GDP divided by distance. We log linearized, and then applying the linear model, there's no problem at all. And the result is very promising. And it's been like more than 6 decades, like old initial model to develop, several decades, and we heavily using it more than 3 decades right now. So it is well known, well discussed, well researched. But there is not that many prior to applying recent developed machine learning model in this field. So I try to do it and see the differences and the limitations and find out what is a new finding is what I want to do during this project. So non-linearity for machine learning side of techniques is good, but as I mentioned before, the limitation of machine learning side is we don't have any idea about how this outcome is coming out. So basically, we're calling it a black box. We don't know the structural relations. We don't know it, but prediction power is good or even accurate, then yeah, we can apply it and we can see some implication out of it. That's the starting point of this project. So what I achieved during this project is, this data set itself is very popular in the gravity model. CPII is a French institute to maintaining and storing all the gravity model variables in their server. So easily well organized with those variables. So it's been an old sets and wrong sets of data, but I am using the 1980s to 2020, getting more recent type of information to get it and compare it. My result is showing that the machine learning substantially overperformed that relative to pooled ORS or fixed effect panel ORS model. So random forest is the best in my case, and neural network is a second. Very small differences out of it. So one measurement is R square. So R square is from the random forest is 0.78. The difference between OLS to random forest is 19%. Generally, without any changes or update or manipulation, just a standard fixed effect model has an issue with R square sometimes, and my data set showing the negative side of R square. In economics, we don't care that much for that as long as the coefficient result is intuitive and the other R squares value is in the range. But I changed it a little bit and tried to develop more in details to the feature selections and everything, and getting like a 0.6 something of R square can be achieved. And next thing I found was neural network applications. Initially, it is not that well performed, but using the hyperparameter tuning, by doing so 13.5% was improved and very close to the random forest, but doesn't have luck to beat the random forest result, which is R square 0.78. And lastly, I tried to getting more interpretability out of this machine learning model. Machine learning models are we considered as a black box and cannot find out any structural relationship among the variables. But I used SHAP to analyze or pin down a little bit in detail. So by doing so, we can say something and getting out some implication out of this. As I mentioned briefly, data source is a CPII gravity database. I used version 2022-11, and it has thousands of bilateral country pair year observations. A main variable they contains are GDP, population, distance, contiguity, common language, FTA, WTO, membership, EU memberships, and a little bit of diversity of how to measure the GDP, population, and also common language like that. So there is some variation of same variable but different measurement. Distance can be changed a little bit of border side of it or distance between the capitals of each countries. But yeah, I generalize it and use it. So it doesn't matter much. I use a standardized and a well-used value instead of, in detail values. And our target variable is trade volume. So I take a logarithm out of it. So trade IJ. I is the origin, like export country, and J is importing country. So destination is J. And I, split the data 50, 22, and 28%. So 1982, 2010 is a training set, validation 2011 to 15, and test set is 16 to 20. But crucially, 34.6% of test observation involving country pair is not present in the training data. So it makes a lot of issue with the fixed effect model. Effect model we'll see later, but also has some issue with non-time varying variable, which is distance is not changing as time goes by. So country geological location doesn't change as time changed. So that makes an issue with R-square negative value in that results. So I totally running 6, even more in the middle of the testing out. So I report 6 model finally. Number 1 is pooled ORS, and second one is fixed effect, and I modify fixed effect variable like a feature selection after that. So core gravity fixed effect model, and number 4 random forest and neural network. I did baseline and then hyperparameter changing by Optuna. Neural network optimized is the last model. So here is the result out of 6 models. Out of sample prediction performance is shown. Test R-square is reported the first column. The number 1 performer was a random forest, 0.78. Neural network after optimized is 0.75. Neural network baseline, 0.66. Pooled ORS is 0.65. Core gravity fixed effect, 0.64 after I took feature selection and then running again. There is other variables if outside of CPII. If I may try, it can drive up a little bit, but I don't think I can make like a 0.7 or something. So this is kind of maximum. Core gravity pooled ORS showing 0.51, and fixed effect gravity original model is negative. Negative R-square is showing like this, 2.72. Basically, the thing is the crucial comments before slide, about 35% of observation is not showing on the training set. So that's driving negative point of R-square. Yeah, I reported to the LMSE, test MAE, correspondingly showing similar type of record as R-square shows. So the best performer, obviously, random forest, and the second one is a neural network after optimization. Yeah, I visualize the model performance trend in this slide. Originally, the one of gravity model showing right here as the 0.04, but it can be improved after feature selection and everything. Then it is close to 0.6 something, but it is way smaller than neural network or random forest. And because of the lack of the numbers, I cannot calculate the RMSE and MAE for the OLS side gravity model. And the right hand side of the panel showing prediction errors. Red one is LMSE, blue one is MAE. So random forest, every measurement, random forest is the best performer we can see. And I plotted in 2 different models, random forest and the neural network. We can see that the dots along the 45-degree lines has random forest has also better prediction relative to the neural network. So the figure itself is predicted relative to actual log trade values. So test set result is coming out right here. Yeah, as you can see visually, random forest predictions relatively tightly around the 45-degree line to the neural network. So here I introduce why standard fixed effect model fails at the predictions is the general phenomenon, and also have some issue with each one of the variable selections, and also some kind of intrinsic issue with the distance value, as I mentioned before. So distance doesn't changing as the time changes. So we have intrinsic trade-offs relationship with the prediction or causality. So I am staying more in causal inference side as an economist, but sometimes as long as the prediction showing more accurate interpretation, then we borrowed that idea to analyze and sending out some messages to the groups, policymakers, or governments like that. Fixed effect models are gold standard in the causal inference side, but in the fixed effect models of error term alpha ij, which pair specific parameter, it cannot be estimated for country pairs not presented in the training set. So it is a fundamental issue with the fixed effect model for prediction. So I tried to, changing a little bit of it, but the variable of distance is the non-time varying variables. So it may have issues, and all other dummy variables like EU members or WTO members, FTA relation, all those things making a strict restriction on the gravity model. So the maximum I can achieve was 0.65. In relative to the 0.04, a massive improvement of the R-square value. Even in the fixed effect model, starting point was negative 2 point something. So huge improvement, but still doesn't have that much prediction power on it. One other issue in the fixed effect model is multicollinearity, which can be measured by VAF. So as you can see, non-time varying distance showing VAF 78. So we decide this severity as higher than 10 or not. And some other, depending on the subject or, field, 0.7, 0.4 is another like heads up values, but it's a huge over than that. So distance is a 78 VAF, and GDP, logarithm of GDP is 47, and the destination has 40. So all those values are severe in multicollinearity. But in some research in economics, we ignore it because we cannot, discard theoretical, firm theoretical support out of this value. So we apply other regression model for this from time to time, but it doesn't have that much big chance of result out of it. So we sometimes are using Poisson estimate or some other regression model. Yeah, if you believe that this VIF is too severe, so just dropping it, changing whole dimension of models. So theoretical importance is make us retention of this variable, and we usually use it, and sometimes we're changing some kind of variables and how to measure it, but still it is not 100% disappear. So I can make some changes and manipulation and other research doing close to the 10, but VIF still have still there in that models usually. So well-known issues in the gravity model. So let's move on to the SHAP analysis. This one is coming out from the random forest result. Shapley additive explanations. This is a Python package. You can easily see SHAP. You Googled it, you can find it. And this is nowadays, well known and widely used, I believe. So we can quantify the contribution of features in the complex random forest model. The originality of Shapley value is also coming out the economics side. The game theorist or economist Shapley made this like 1960 around, and originally it is developed to analyzing the situation of cooperative game. And recently we're using a lot of measuring that the teams or some situation that somebody cooperate as a team, team outcome can be how we can distribute the payoffs out of game results, how wisely, efficiently distribute that result is coming out from the Shapley model. And recently, it draws a lot in the deep learning side too, and even AI side to measuring or training the AI agent. So how we can giving out the reward from the AI's performance, AI agent's performance to measure that and giving out the result or reward we measuring with the Shapley value. And as we can see, the technique, the after the random forest result, Shapley value showing, this summary table, GDP product, which is multiplication of GDP origin and GDP destination itself is most production power in the model. And second one is a GDP of origin and distance between the countries and population product, which is population of origin and destinations and distance, different measure of distance and distance of capital and GDP of destination country, population of this destination country, correspondingly like that. We can make the order higher feature value to the lower value you can see. So we can conclude that GDP product dominate the prediction, which Newtonian gravity equation telling us similarly applying to trade volume, we can say. So the assumption and the gravity model itself is not wrong at all. And there is the reason why we keep using gravity model in the trade field to see how to trade volume is determined. And we're adding other, independent variable in the model and to see to the control of this, original trade volumes can be determined by given variable as GDP and also distance, and adding other, variables, tariff values, or sometimes membership of FTA, membership of EU, or those other variables, and then say that how much power to changing of, trade volume can be analyzed. So basic line of that control variable as a GDP and distance can be justified by random forest model too. And comparison across the methods, we using the machine learning models are relying on, correlations. And even though it is covered by, mysterious box, a black box, but background or explanation power of or justifying the old gravity model is right here and showing the results. And I summarize feature importance comparison with the table. Also brought up the Gini index. Gini index also well used in economics side to measuring the income inequality, wealth inequality, but it can be applied to machine learning side too, to showing which one is more important feature in the model. So the big there is not that many big differences out of each one of the measurement. Gini and Sharp showing similar pattern, but sometimes showing a little different of results. So Gini value showing the GDP product is number one, and Sharp also showing number one, and number two has the same ranking as the GDP of origin, and number three for Sharp GDP destination, but Gini side is number 4, and distance is number 8. Relative coefficient analysis where for the gravity model, everything is very significant, like 0.5% of significance of that value, and intuitively showing right direction of coefficient value. So GDP positively working, GDP destination also positively working, distance is negatively working, and the membership of FTA showing positive. So if the two country has a free trade agreement together, then it will boosting trade volume positively. To sum up, GDP variables dominate across Gini, Sharp, and ORS coefficient, and machine learning model naturally captured interaction of bilateral economic mass, which is GDP product. Now we can see local interpretability using the SHAP waterfall plots. So basically, the average of FX, which is the trade volume, is a 10.391, which we can see on the x-axis of each one of the graph. FX is top of each one of the three graphs, showing 10.221, 9.103, 105, and 4.683. So the value itself is changing by the side of bigger country and higher trade volumes cases, and relative to the small cases is looking right here. And how much each one of the variable contribute the change from the expected value to final value. So first the graph showing each one of the features, how much acting as expected value to changing the other variables. As you looking at as LM population destination, positively change it to the 10.391 as expected value of outcome to, changing 0.028 side of it, and the distance is negatively working to the change of negative 0.24, and the distance of other measurement is negative 0.21, and GDP product is working 0.2 to the positive corresponding. Same thing happened in the different scenario, middle volumes of GDP countries, how they we can expect of each one of the changes with the variables. So in this case, even though final prediction is 9.105, which is smaller than 10.39. In this case, even in the GDP origin working positively, moving the value 1.08, but other values are negatively working in that direction. And in the middle of that, there is a positive GDP differences and population of origin, EU members, and GDP product. All those things is positively working with the smaller side of magnitude. And a very small country side of expectations, the expected value is 10.38, but the final value we estimate is 4.68, dramatically reduced, which is the size is smaller, and among those scenario, what is happening? So GDP product is negatively working 1.78 in this case. Smaller country showing all those values are negatively working. It is pinned down one of each scenarios and showing how much each variable is working to the change of expected value to the final prediction point. So we can see that how each features move the prediction from the baseline expectations to the final forecasting. So this one can give us some insight to interpretability of machine learning model. Without it, we cannot say much of each one of the changes, but we categorize the subgroups and finding out some different scenarios and looking at the value changes correspondingly. So now it's time to sum up and conclude this presentation. Let me summarize of the findings. Machine learning, particularly random forest, the output is really good relative to the traditional econometric modeling. So 78% versus 66% after doing all those feature selections and then try and adders and update all the values, the selection of the variables. The interpretability is coming out from the SHAP side of predictions. So using that more wisely and more interesting patterns, we can find it, we can say some more insight out of it. So each one of the groups, like policymakers or businesses, we say that the machine learning based forecast for export, selection, market selections, and planning for that, what kind of country we should, targeting on, can be given with this prediction results. In the economist or research causality side, traditional fixed effect is must have and gold standard. Sometimes we can change the data set, and sometimes we can adding more variables outside of CPII setups. We can get the better results. So future we can do some more specific, sector like semiconductor industry or AI industry or even like agriculture product industry, categorize each one of the different industry and then can analyze it to get the better results out of it. So here's my final conclusion. The future of trade analysis lies in using machine learning for forecasting or predictions. But still, we need causal inference in the original ORS or some other techniques is necessary. And even more like a Sharpe values or other technique for the better interpretation will help. And having some insight and using all those models together have improvement out of these data sets. So as far as I know, 78% of accuracy in prediction, we can deliver that, and we have some kind of guidelines to change our causal inference model to or update or modified or feature selections, all those technique we are using, and then we try to upgrade or improve the results out of it. And also sometimes I get some insight out of like a random forest feature selection, which variable have more relationship, like not even in the correlation side, but we know which variable is higher feature importance. So by doing so, referring that, we can setting up the model a little bit differently and getting, or saving time, better model, efficient model out of it. So finally, I really appreciate this semester to learning a lot of machine learning model and neural network model, all those different kinds and how it is applying recent word. It is really fun and enjoyable experience for me to extending the perception of how we approach certain matters. Even in economics, we need to have some knowledge and research on how to extending model selections, even in the machine learning or deep learning side of it. Thank you.